In this video, I want to show you how to construct the so-called Wigner matrices. These are important matrices, for example, in loop quantum gravity to describe some states in loop quantum gravity. These kind of matrices appear. But anyway, here in this case, I want to focus on the math and how to construct these matrices, how they arise from SU2, from the SU2 group. In particular, we start from a spinor. So a spinor from the fundamental representation has two components, let's say xi and eta. And we call, for example, this spinor, so this is a row vector, and therefore I can call it chi dagger. If we act on the right with a unitary matrix given by the elements A, B, C, and D, we can call this matrix U. What we obtain is some kind of rotated spinor, and I can call the components of the spinor xi prime and eta prime. We can call the spinor chi prime dagger. If you want, you can also rewrite this same equation like this: chi prime equal to u dagger chi. So u dagger is another unitary matrix. You can call this W, whatever you want to call it. You could have called this one u dagger and this one u. Doesn't really matter. This matrix should comply with the constraint that u dagger u is equal to u dagger is equal to the identity, and also that the determinant of u is equal to 1. So in general, what we are going to do is something that is not really dependent on these constraints, so we will be a little bit more general, but you have to think that we are really interested in the SU2 case, and for SU2 we have these constraints as well. So these, in general, these constants, these parameters, they are complex parameters, so they have a real part and an imaginary part. So from here you actually have 8 parameters, 8 real parameters. But due to these constraints, what you get in general from the theory of SU2 is 3 independent parameters, scalar parameters, real parameters if you want, parameters. And for example, these 3 parameters are related to a rotation in 3 dimensions, right? So you can think of U also as some kind of rotation. It is related to the rotation group in 3 dimensions. And what I want to do now is first let me write xi prime from this equation here. Xi prime is equal to A xi plus C eta, and then we have eta prime equal to B xi plus D eta. So we have an equation that relates xi and eta to xi prime eta prime after the so-called rotation, quote unquote rotation. And now I want to write down some polynomials of the following kind. Let me write down the expression pjm. So the polynomials depend on two numbers, j and m, where m is equal to minus j plus 1 dot 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 all the way up to j. So we have 2j plus 1 possibilities. And this is also related to all the possible states that you have for a spin j particle, for example. And this polynomial is a polynomial that depends on xi and eta. And I define it to be of the following kind. It is a polynomial of degree 2j. You have xi to the j plus m and eta to the j minus m. And then we divide by a factor, and I will show you why we have this factor, j plus m factorial, j minus m factorial. And these two factors are inside this square root here. You can see that when you let m vary, you can obtain 2j plus 1 different polynomials. You can see it from here because m can take 2j plus 1 values. Now, what I want to do is I want to write down pjm of xi prime eta prime. So it is a polynomial of the rotated variables. And I want to expand it as a sum over m prime of pj m prime xi era, and then I have some coefficients dj m prime m of u. So this will be a function of the group u. And in particular, these are indeed the Wigner matrices. So if we fix this J, we get a matrix because we have two indices here, and we can interpret these coefficients as matrices. And you can see that we have expanded the rotated polynomial, if you want. We call it quote-unquote rotated polynomial in terms of the unrotated polynomials multiplied by these Wigner matrices. So it's as if we are acting on the right with these Wigner matrices that basically generalizes the formula that we have written here. So instead of u, we have the Wigner matrix related to the spin j representation, and instead of the spinner, we have this polynomial that is related to spin j, as you can see. So it is some kind of generalization. And now what I want to do basically is I want to rewrite the formula for this, which you can see from here. Basically, it's exactly the same formula, but you have to replace xi with xi prime, era with era prime, and we want to expand it in such a way that we can find these matrices. Now, if I write the numerator here, I want to write this numerator here, where I have xi prime here and era prime here. But remember that I also have a formula for xi prime and era prime in terms of xi and eta. So that's what I want to do. I have something like this. I have a xi plus c era to the power j plus m. Then I have b xi plus d era to the power j minus m. Now, I want to use a formula, which is a well-known formula. In particular, it's the binomial theorem. Basically, I have, for example, x plus y to the power n. We can write it as summation over k equal to 0 to n x to the power n minus k, y to the power k, and choose k. But there is also another way to write the same formula, which is the following. So we can sum over n1, n2 greater than or equal to 0, such that n1 plus n2 is equal to n, and then here we get n factorial divided by n1 factorial, n2 factorial, and then I have x to the power n1 and y to the power n2. I want to use exactly this formula in here, so I have to expand this, and I also have to expand this. So let me zoom out a little bit. I have j plus m factorial that I can factor out, j minus m factorial, and then I have a summation over n1, n2, n3, n4, all greater than or equal to 0, and then we have to satisfy some constraints, in particular n1 plus n2 equal to j plus m, and n3 plus n4 equal to j minus m. And then in here I have xi to the power n1, c era to the power n2, b xi to the power n3, and d era to the power n4. We have to divide by n1 factorial, n2 factorial, n3 factorial, n4 factorial. At this point, if we introduce another parameter, which I call m prime, and we assume that n1 plus n3 is equal to j plus m prime. So this is just another way of manipulating this same summation. So I want to manipulate it slightly differently. And so if this is true, and you can take this as a definition of n prime in terms of n1 and n3. By taking this for granted, we also have another way of writing n2 plus n4, because n2 can be written, for example, from here as j plus m minus n1 plus n4, which we can rewrite from here as j minus m minus n3. And at this point, you can see that we can write this as 2j. This m will cancel this m, and then I have minus n1 plus n3. But n1 plus n3 is equal to j plus m prime. So here we substitute j plus m prime. So we can write this as j minus m prime. So n2 plus n4 can be written as j minus m prime, and n1 plus n3 can be written as j plus m prime, like this. So we can rewrite this formula in another fashion. I'm going to write it as j plus m factorial, j minus m factorial. Then we have a summation over m prime over all the possible values of m prime, which are minus j all the way up to j. Then we have another sum over n1, n2, n3, n4 greater than or equal to 0. We have n1 plus n2 equal to j plus m, which is the same as this condition here. Then we have also fixed another condition, which is n1 plus n3 equal to j plus m prime. And then I have another condition, n3 plus n4 equal to j minus m, which is exactly this one. And we have n2 plus n4 equal to j minus m prime. Here we have a to the power n1, c to the power n2, b to the power n3, d to the power n4, and then we divide by n1 factorial, n2 factorial, n3 factorial, n4 factorial. And outside the summation, we have xi to the power j plus m prime and eta to the power j minus m prime. So this is convenient. So it's convenient to write it like this, because now we can see that we have these terms that appear in the definition of pjm. We simply have to divide by this factor, which we also have to do on the left. So we also have to divide this one by a similar factor there. It's similar, it's not the same, because here we have m, whereas on the right we have m prime, as you can see. So it's quite simple to rearrange the terms there. So you divide this one by this factor here, and instead of m you have m prime. So if you want, I can do it here. So I divide this by the square root of j plus m prime factorial, j minus m prime factorial, and of course I have to multiply by the same thing. So let me cancel this equality. I will put it here. So here I have the square root of j plus m prime factorial, j minus m prime factorial, and then I also have to divide the quantity that we have on the left, which is this one. We have to divide it by the square root of j plus m factorial and j minus m factorial. And of course, this one here will become a square root, right? Because if we divide this by the square root, on the right, we also have to divide by the same thing, and we can rewrite what we have on the right in this way. So we actually have only one square root with all these terms inside, if you want. It is just another way of rearranging this, right? Now, written in this form, we have found basically the Wigner matrices, an expression of the Wigner matrices, in particular dj m prime m of u, where of u means of A, B, C, and D. So A, B, C, and D describe u. Therefore, when I write D as a function of u, I'm writing D as a function of A, B, C, and D, the parameters of the group. And now let me also do another thing. In particular, we are going to relabel some of these indices. N2 will be labeled as N3, and N3 will be labeled as N2, just for the sake of convenience, because in this way, I mean, it is just another way of writing this. Instead of writing ACBD, I'm going to write ABCD, and these two will simply change their order. So we will have B to the power N2 and C to the power N3. It is simply a different way of writing it, but it's the same thing. Let me write down the expression. We have the square root of all these terms, j plus m prime factorial, j minus m prime factorial, j plus m factorial, j minus m factorial. And then here we have just one summation. It's this summation here. You don't have to put this one here because you have to remember this formula. You have a summation over m prime here, so this summation over m prime will not be contained in the definition of the Wigner matrices there. It's easy to convince oneself that this is the case. So you have summation over n1, n2, n3, n4 greater than or equal to 0. We have n1 plus n2 equal to j plus m prime, n1 plus n3 equal to j plus m. Remember that I have changed the role of n2 and n3, so I have relabeled them in the opposite order. So n2 will become n3 and n3 will become n2 in this formula here. So you can see that these two conditions will become these two conditions here, and then these two conditions here will become n3 plus n4 equal to j minus m prime, and n2 plus n4 equal to j minus m. And then in here you have a to the power n1, b to the power n2, c to the power n3, d to the power n4, and then we divide by n1 factorial, n2 factorial, n3 factorial, and 4 factorial. So this is the complete expression, and it's the one that we wanted to find, of Wigner matrices. In particular, they are expressed in terms of the parameters A, B, C, and D, right? In general, we could also rewrite it in terms of angles, if you want to be more specific, because a group, a generic group, an SU2 group, can be written, for example, in exponential form, e to the minus I, then we have something like this, psi over 2 n dot sigma, where sigma is the vector of polymatrices, so it contains three components, the three polymatrices, whereas psi is a certain parameter and n is a unit vector. So there are three independent parameters. One is here, and n has two independent parameters. For example, two angles, because n is a unit vector. It has three components, but the three components should satisfy a certain constraint, such that the norm of the vector is equal to 1. So we have three independent components overall, right? This complex exponential can be expanded if you want, so you can write it as a series, n equal to 0 to infinity, then we have minus I psi over 2 n dot sigma to the power n, and then you have 1 over n factorial, and you can rewrite this series over the even integers and also over the odd integers if you want. It is convenient to do so because this expression can be simplified, in particular by using some properties of the polymatrices. For example, n dot sigma squared can be written in index notation as ni sigma I and j sigma j, where you sum over I and over j. This can be written as 1/2 anti-commutator between sigma I and sigma j and I and j. But the anti-commutator of polymatrices can be written as 2 delta ij, the Kronecker delta ij, times the 2 by 2 identity. Therefore, this is exactly equal to norm n squared times the identity. But the norm of n squared is equal to 1. So we see that this is equal to the identity. And similarly, if you raise this to the power 4, 6, 8, and so on. So we can simplify the powers of this kind of matrices because this is a matrix. You have a dot product between a vector and the matrix, which you have interpreted like this: n1 sigma 1 plus n2 sigma 2 plus n3 sigma 3. But this is a matrix because each of these terms is a matrix, right? So indeed here you have the identity, as you can see, but sometimes it is also possible to use shorthand and write it as 1 for the sake of simplicity, but you have to remember that what you have here is indeed a matrix. And then when you expand this in terms of the even integers and the odd integers, it is quite easy to convince oneself that the sum over the integers will be simplified like this. The summation over the even integers can be simplified by considering this property and also the simple property that n dot sigma to the power 0 is equal to the identity. It's quite trivial. So this will become minus I psi over 2. N dot sigma can be replaced by the identity if you want. So I'm not going to put anything here to the power n 1 over n factorial. But also the summation over the odd integers can be simplified because if you raise it to the third power, for example, if you have n dot sigma to the third power, this is equal to n dot sigma, right? Because n dot sigma squared is equal to the identity. So this is what you get. And therefore, what you get in here is something like this. You have the summation over the odd integers. You have 1 over n factorial minus I psi over 2 to the n, and then outside the summation you have n dot sigma. So the complex exponential, which is a complex exponential of a matrix, can be written as cosine of psi over 2, which multiplies the identity, minus I sine psi over 2, which multiplies n dot sigma. So it becomes a much more manageable expression because in here you don't have an exponential of matrices and you don't have an infinite summation. So you have a finite number of operations to perform, and these kind of operations are quite simple. So in particular here you can see that you have two independent parameters from here, from the unit vector, and you have another independent parameter from here. So this is how you can write u. Remember that u contains the parameters a, b, c, d, and from this equation you can write a, b, c, d in terms of the three angles that you have here, right? And you can write down a formula for a, b, c, d in terms of these three angles, and therefore you can also write Wigner matrices in terms of the three angles. Another way to write Wigner matrices, which is actually probably the most common, is to write U in terms of the so-called Euler angles. Euler angles. In particular, you write U as a product of three rotations. You apply three different rotations. You have one rotation around the z-axis, so you have something like e to the minus I alpha over 2, so you have the parameter alpha, which is an angle. Sigma 3, here you have sigma 3, which is the polymatrix along the z-axis if you want, so it's the third component of the vector sigma. That's why this one should be interpreted as an angle around the z-axis. Then you have a rotation around the y-axis, so you have something like e to the minus I beta over 2 sigma 2, and then you have e to the minus I gamma over 2 sigma 3. So you have a rotation around z, a rotation around y, and another rotation around z. So you have z, y, z, something like this. So this is how you can write a generic rotation. If you think about it, this is a generic rotation. You could have chosen sigma 1 if you want, but this is how you usually define Euler angles. And in general, you can obtain a generic rotation from something like this by applying three distinct rotations around the three axes z, y, and z again. Now you can use the formula that we obtained in here to express, for example, this matrix. This is an exponential of a matrix, and it is a matrix because it's a sum, it's an infinite sum of matrices, so you obtain a matrix, 2 by 2 matrix. This exponential can be written as the cosine of alpha over 2 minus I sine alpha over 2 sigma 3. And similarly, you can express this one as cosine of beta over 2 minus I sine beta over 2 sigma 2. And similarly, you can express this one as the cosine of gamma over 2 minus I sine gamma over 2, and then you have sigma 3, and you can multiply them. Remember that these terms multiply the identity, the 2 by 2 identity. It is possible to multiply them. It's very simple actually to multiply them, to multiply these matrices. You have to remember how to write sigma 3 and sigma 2. They are just Pauli matrices, 2 by 2 matrices, and you do some basic operations and you write down a formula for u in terms of the Euler angles. Now, I'm not going to do it because it's not the point here, but basically we have u that can be written in terms of the parameters a, b, c, and d. And after you do these operations, you have some formulas that you can write down, quite simple formulas, to write a, b, c, and d in terms of the three angles alpha, beta, and gamma. So you can write alpha, beta, and gamma instead of a, b, c, and d, or the cosine or the sine of these angles, or the complex exponentials of those angles, and you can replace them basically in this formula, so you can write Wigner matrices in terms of the Euler angles.